All right, let's dive right into this high-yield explainer on Chapter 448. We're looking at the incredibly dense but absolutely fascinating pathology, clinical manifestations, and genetics of ALS and other motor neuron diseases. Today, we're going to unpack what is arguably one of the most devastating neurodegenerative disorders known to medicine and really get into the exact molecular mechanisms that drive it.
To make sure all this information actually sticks, we're doing a complete anatomical to molecular drill down today. Our agenda is simple. First, pathological hallmarks. Second, clinical manifestations. Third, critical differential diagnoses. Fourth, genetic pathways in ALS. And finally, number 5, other motor neuron diseases. So let's start with a defining question to really frame this disease. Why on earth does ALS selectively destroy the motor system while completely, and I mean completely, sparing sensory, bowel, bladder, and cognitive functions? You know, ALS is just uniquely cruel precisely because of this selectivity. As the motor neurons degenerate, things like the sensory apparatus, the cerebellar structures, and those parasympathetic neurons in the sacral spinal cord that control your bowel and bladder sphincters, they remain completely intact. The patient is fully aware, yet physically trapped. Though, as we'll see in just a second, there is one very specific exception when it comes to cognition. Let's jump into Section 1, Pathological Hallmarks.
Okay, the absolute foundational concept you need to grasp here is the dual destruction of both upper and lower motor neurons. Think about it. You've got your upper motor neurons originating up in layer 5 of the motor cortex, heading down via the descending pyramidal tracts. Then you've got your lower motor neurons, those anterior horn cells in the spinal cord and their brainstem homologs. Well, in ALS, both of these populations die off. Actually, without clear clinical involvement of both the upper and lower motor neurons, an ALS diagnosis is pretty questionable. The death of these cortical and peripheral motor neurons is literally what leads to that secondary tract thinning and severe muscle denervation we see at the bedside.
Now remember that vital caveat I mentioned about cognitive sparing? That's the ALS-FTD connection. While cognition is usually spared in classic ALS, in a specific subset of cases, the disease actually arises concurrently with frontotemporal dementia, or FTD. In these patients, we're seeing degeneration of the frontotemporal cortical neurons right alongside that motor neuron loss, which shows up as distinct cortical atrophy. It's just a crucial clinical connection to keep in mind, because it really highlights how these neurodegenerative pathways can overlap.
Moving right along to Section 2, Clinical Manifestations.
If you only take away one thing about the clinical presentation from this explainer, let it be these hallmarks. The classic presentation starts insidiously. Usually, it's this asymmetric distal weakness. That's the very first sign. Patients will often complain about cramping with volitional movements, especially when they're stretching early in the morning. Then, because of that lower motor neuron denervation, you start seeing spontaneous motor unit twitching, which we call fasciculations. That comes along with profound muscle wasting, or amyotrophy. But hey, remember, both upper and lower neurons are taking a hit here. So right alongside that flaccid wasting, you're getting upper motor neuron signs too. Hyperactive reflexes, spasticity, and severe bulbar symptoms like dysphagia and dysarthria. It creates this incredibly unique and really devastating combination of flaccidity and stiffness in the exact same patient.
A super specific bulbar symptom you definitely need to note is the pseudobulbar effect. As the upper motor neuron damage progresses, specifically, we're talking about the degeneration of corticobulbar projections that innervate the brainstem. Patients literally lose the ability to modulate the physical expressions of their emotions. So this results in involuntary and often wildly exaggerated bouts of weeping or laughing. And the wild part? It doesn't even necessarily match the patient's internal emotional state. It's just a direct mechanical result of that descending tract degeneration.
All right, Section 3, Critical Differential Diagnoses.
So, because ALS is currently untreatable, the absolute most crucial point here is that you cannot afford to miss a treatable mimic, period. Let's look at a big one, cervical spondylotic myelopathy. Say a patient has osteophytes compressing the cervical cord. They can actually present with lower motor neuron signs in the arms, think wasting and fasciculations, and upper motor neuron signs in the legs, like spasticity. It perfectly mimics ALS, and that right there is why getting an MRI of the cervical spinal cord is absolutely mandatory. Next, you've got MMCB, or multifocal motor neuropathy with conduction block. Now, this is predominantly a lower motor neuron disease, but your golden ticket here is electrophysiology. It's going to show a conduction block, which you just don't typically see in classic ALS. And of course, always screen for environmental and systemic mimics like lead poisoning or thyrotoxicosis, because those can easily present as secondary motor neuron diseases.
Let's zoom in even closer for Section 4, Genetic Pathways in ALS.
Now, while familial ALS, often called FALS, only makes up about 5 to 10% of total ALS cases, the specific genes involved give us a massive, really incredible window into exactly how these motor neurons die. Take a look at SOD1. This accounts for about 20% of familial cases and creates this toxic gain of function just from protein instability. Then you have TAR-DBP, which encodes the TDP43 protein, and FUS/TLS. Both of these are absolutely critical for RNA and DNA binding and metabolism. We've also got UBQLN2, which is tied to protein degradation pathways, and ALS2, encoding a protein called alsin. That one is actually linked to a juvenile onset form of the disease through defective GEF signaling. So what does this all mean for us? Well, these genetic clues are basically screaming that protein misfolding, defective RNA processing, and impaired transport are the ultimate executioners of the motor neuron.
But listen, if you only remember one single genetic mutation from this entire explainer, it has to be C9 or F72. This is hands down the single most common familial ALS mutation. We're talking nearly half of all familial cases and a really significant chunk of those ALS-FTD overlap cases we talked about earlier. It involves this expanded GGG-CCC hexanucleotide repeat. Basically what happens is these massive RNA repeats undergo non-canonical translation across all reading frames, and that generates these lengthy, highly toxic dipeptides. And the really wild part? We can actually detect these dipeptides right in the patient's spinal fluid. It acts as a totally unique biomarker for this specific variant of ALS. How cool is that?
Which brings us to our final section, number 5, other motor neuron diseases.
When we step back and contrast these other diseases, your key takeaway should always be exactly which neurons are being targeted. Because unlike ALS, which as we know destroys both, things like Kennedy's disease and spinal muscular atrophy only target the lower motor neurons. Period. Now, on the exact opposite end of the spectrum, you have primary lateral sclerosis, or PLS, and hereditary spastic paraplegia, or HSP. These exclusively target the upper motor neurons. In HSP, for instance, this is driven by mutations in genes with names like spastin, atlastin, or paraplegion. And since PLS and HSP completely spare those lower motor neurons, you simply are not going to see the fasciculations or amyotrophy that are so classic in ALS.
Let's take a slightly closer look at Kennedy's disease, also known as X-linked spinobulbar muscular atrophy. Contrasting this against ALS gives us a massive real-world diagnostic clue. See, Kennedy's is caused by CAG repeats in the androgen receptor gene. So right alongside that pure lower motor neuron weakness, you also get profound androgen insensitivity. If you see endocrine symptoms like gynecomastia and reduced fertility in a male patient who's also presenting with lower motor neuron weakness, well, that is a dead giveaway. You're dealing with Kennedy's disease there for sure, not ALS.
Similarly, spinal muscular atrophy, or SMA, gives us yet another vital piece of this puzzle. SMA is typically an early onset, just devastating loss of lower motor neurons. The genetic culprit in this case is the SMN gene, which, appropriately enough, codes for the survival motor neuron protein. Losing this protein entirely disrupts the trafficking of RNA complexes right across the nuclear membrane. This disease brilliantly illustrates just how incredibly sensitive our lower motor neurons are to literally any disruption in cellular transport or RNA processing.
So stepping back from the asymmetric weakness we see at the bedside, all the way down to those tiny GGGGC repeats of C9 or 72 hiding in the nucleus, the puzzle pieces of motor neuron disease are slowly but surely falling into place. We are mapping these genetic pathways from RNA transport defects to toxic protein accumulation with unprecedented clarity. But of course, the ultimate question still remains. How close are we to actually translating all this molecular understanding into real targeted neuropharmacological cures for ALS? Could fixing these upstream mechanisms finally halt this devastating decline once and for all? It is an absolutely fascinating frontier in neurology right now, and one that holds immense hope for the future. Thanks for exploring it with me.